Okay, so there's one application for this called the polymer-derived ceramics is anti-corrosion and anti-fouling. However, we have to modify its surface property. Okay, so as we know that a low surface free energy, which has the antibacterial effects. Okay, therefore, this research we're gonna focus on how to modify the polysilanze pre-ceramic precursor incorporated with the fluorine complex. Okay, just use the fluorine complex to modify its surface property, its surface free energy. Okay, therefore, as we know that there's some hydrophobic surface in nature, such as lotus leaves and butterfly wings. And of course, there's an application in our daily life, such as the prevention of the adhesion of snow and the stain resistance and the self-cleaning windows. And those hydrophobic applications provide our daily life more easier. That means we don't have to clean those like windows or clean this jeans frequently, right? And the other issues with the concern is the corrosion effects. Okay, for the ships, are inevitable polluted by the oil pollution, or there's some microorganisms in ocean. Those will attach or will stick to the ship's body, right? And those pollutions or microorganisms stick to the ship body will reduce the speed of the cruise. Okay, will reduce the cruise of the ship's cruise. Therefore, how to prevent from those pollution or the microorganism attached to the body is the other issue we have to concern, right? For this modifying the surface free energy or the surface property. Okay, of course, the corrosion, as I mentioned that. For the ships immersed in the ocean, right? The ocean's like an electrolyte, right? And for the long term, this electrolyte relates to corrosion in the ship body, and it will shorten the maintenance interval. That means the maintenance cost increase a lot, right? If the ship body corroded, right? So for this research, I'm going to focus on two function, or we can call it the dual function. A dual function low surface area coating. So what's the dual function? One is the anti-corrosion, and the other is the anti-fouling. Okay, and the materials we're going to use is the called the PDC. That's I already introduced a lot previously, right? In few previous spatial talks. And the precursor is a polysilanze pre-ceramics precursor, and it can be easily deposited on different type of substrate. Okay. And in this case, we're using the it's called a polysilanze. That means this structure has the silicon nitrogen bond right here. Okay. Silicon nitrogen bond here. Okay. If the precursor has polysiloxane, that means we have these silicon oxygen, right? Silicon oxygen bond right here. Oh, sorry, I made some mistakes. I have to correct it. It's a silicon nitrogen bond. Okay. So it's a silicon nitrogen bond. Okay, and the silicon nitrogen bond contained with boron. Okay, contained with boron. Okay, so therefore the precursors depends on what's the bonding between the silicon and its functional group or no. Okay, for the coating techniques of PDC, the techniques includes dip coating, spinning coating, spray coating, and so on. It depends on what kind of the surface you have it. Okay, if the surface is not uniform with the complex shape, maybe the spray coating is the optimum technique. Okay, for the uniform coating on a complex surface. Okay, if the surface is porous, well, maybe the dip coating is more suitable. Okay. And the polysilanze precursor, pre-ceramic precursor, can be commercially available from Merck. Okay, and it's chemical structure. Okay, that's I already mentioned previously that it's silicon nitrogen bond. Okay, silicon nitrogen bond with different functional group and contain the hydrogen. Okay, and the polysilanze provides high thermal stability and oxidation resistance and very good corrosion resistance. Okay, after pyrolysis, of course, after pyrolysis. And there's some applications of PDCs like the automotive rotors and some sensor. Okay, some semiconductive sensor. Okay, it's already commercialized. It's already been commercialized. And the fluorine is compound. The fluorine is the lightest elements in the halogen and because fluorine is electronegative and it has the greatest attraction for electrons, which leads to form compounds with other element easily, right? And the property of the fluoropolymers are largely derived from the spatial features of carbon fluoride bond, and it has one of the highest bonding energy. And this highest bonding energy results in low polarization of carbon fluoride bonds, and in terms of imparts a range of important properties such as low solubility, low friction, and high thermal stability and strong chemical resistance. Okay, and this fluorine complex that we use is from the Duravanc's AF340, okay, from Rayong, Taiwan, and it's a fluorinated polysilanze rinsing. Okay, and this shows its chemical structure of this fluorinated resin. Okay, and then when the polysilanze pre-ceramic precursors incorporate with this F340, it can cross it with the pre-ceramic precursor at room temperature and can prevent from the infiltration of water and other liquids and improve the acid and, and by its resistance, so on. And the other materials I'm going to introduce is the titanium dioxide, which represents a type of the broad spectrum bactericide that with excellent biocompatibility and the corrosion resistance. Okay, and the activation of TiO2, the titanium dioxide particles with the accredited UV lights generates electrons and holes that react with the absorbed water and the dioxygen molecules to form the RS, the reactive oxygen species that can kill and inhibiting this growth of bacteria. Okay, and why I introduce this TiO2 is mean I'm gonna incorporate TiO2 with this polysilanze pre-ceramic precursor, and let's look at what its surface property is. Okay, there's an experimental. We measure the contact angle. Okay, with the different surface of the polysilanze precursor incorporates fluorine or dilute or incorporate with titanium dioxide. And we calculate the surface energy by the OWRK method. Okay, so you can look at this and we measure the contact angle And we use two types of the liquid. One is the water, okay, which is the polar solution. Okay, the polar solution. And the other one is the diiodomethane, which is the dispersed solution. Okay, therefore we can calculate, we can measure this contact angle of the surface, and can use this table use this table and find out this surface energy of these two types of liquid, polar and not polar, polar and dispersed. And we can calculate the surface free energy. We can calculate surface free energy. Okay. And then we use the three electrode system to measure its anti-corrosion ability. Okay, so the working electrode is the copper coated with the polysilanze pre-ceramic precursor incorporated with the fluorinated resin or other things and so on. And the counter electron is the platinum, and the reference electrode is silver chloride. And we use the 0.5 mole of the sulfuric acid. Okay, we have the fixed scan speed. And we can find out the Tafel curve, okay, if we figure out the tangent of the anodic and the cathodic polarization curves, we get the intercept right here, okay? And then we can find its corrosion current and the corrosion potential. Of course, what we desire to get is the lowest, as low the corrosion potential is better, right? Sorry, that's my wrong. I have to correct it. As the higher corrosion potential is what we want, and the lower corrosion current that I want, right? Okay, and then we can calculate its polarization resistance, corrosion rate, and by the equivalent weight. Okay. And then we use the nano indentation to figure out its surface mechanical surface property. Okay, except for the anti-corrosion and anti-fouling, we have to realize whether the surface is relatively strong. Relatively strong. Of course, it might not be stronger than some metals or alloys. However, we have to realize whether it's strong enough. Okay, there's what we use the nano indentation to figure out its surface mechanical property. That means we have indentation tips, the diamond tip, pyramid tips, okay, to indent the surface of the polysilanze pre-ceramic precursor after curing, after pyrolysis or curing. Okay, and from its load and displacement curve, we can figure out whether this surface is strong enough or not. Okay, so the sample that we prepare list here, and this means the 100%, the pure polysilanze pre-ceramic precursor. Okay, and this represents the fluorine compound F340. Okay, the pre-ceramic precursor incorporate F330 with X weight percent. Oh, sorry, white weight percent. Okay, so for this, PSD as 100 means the 100% of this precursor. Okay, and in this case, it means the X weight percent of the precursor and the Y weight percent of the fluorinated resin at 340. Of course, we dilute it with the in acetone. Okay, the same we have the 100% of the pure polysilanze preceramic precursor, and we have the diluted weight percent of the solution, and also we have the X weight percent of the TiO2, okay, mixed with the preceramic precursor. Okay. Therefore, we can figure out the contact angle of the pure, right? Pure precursor, pure preceramic precursor. We find out the highest contact angle is at the 500 Celsius, right? When the this cross-linked or the paralytic temperature is higher than 500, its contact angle drop substantially. Okay. Therefore, our experiment will operate below the 500 Celsius. Okay. And then we can find out that that's the precursor incorporate with the F340. Well, this contact angle increase significantly. Okay, within the temperature range between 200 to 300 Celsius. Okay, and the contact angle increase from 94 to 111. Okay. However, when this temperature, this the current temperature reach to 500, well, it seems not, this contact angle seems not increase a lot. Okay, it's almost the same, not change a lot. Okay, and when the temperature reaches 500, well, there's no big difference between the fluorinated or non-fluorinated, polysilanze preceramic precursor coating. Okay, and then we can calculate. The reason why is that this fluorinated, the fluorinated resin, this fluoride complex, is decomposed with a temperature higher than 300. Okay, decomposed. So the fluorinated will decompose when the cross-link temperature higher than 300. Okay, that means we cannot find any hydrophobic effect from those fluorinated compounds. Okay, and then we calculate the surface energy. Okay, we figure out that so the surface energy of silicon wafer is about 46.47 millijoule per meter square. Okay, and we spin coated this fluorinated compound. We find out the lowest surface energy is 28.43 when the cross-linking temperature is 200 Celsius. Okay, so I will just mention that when this surface energy below 30 millijoule per meter square, that's the antibacterial effect generated. Okay, so this is the boundary, is a limit right here. It's a limit right here. Okay, if the surface energy is below 30, that means the surface can be antifouling or antibacterial. Okay. Okay, I just show you that when we dilute it, when this polysilanze precursor diluted by acetone. Okay, we find out that its contact angle increase, right, at 400 and 500 Celsius. Okay, and it almost reaches 122 degree. Oh, I forgot to mention that for the hydrophobicity, that if the contact angle is less than 90, that means the surface is hydrophilic. And when this contact angle is higher than 90 Celsius, 90 degree, that's mean this surface is hydrophobic. Okay, of course, when this contact angle, well, there's different criteria. Some, someone will say when this contact angle higher than 120 is called super hydrophobic, and some will say, okay, it has to higher than 150 degree. Okay, the contact angle has to be higher than 120 degrees. Its hydrophobicity belongs to super hydrophobicity. Okay. And so we can predict or speculate that for the temperature below 300 Celsius, it's the silicon hydrogen bond formed with the low polarity. When this temperature, crosslink temperature higher 300, it's high polarity. Okay, it's silicon hydroxide or silicon oxygen silicon. Okay. And we compare the surface energy of the pre-ceramic precursor, incorporate the titanium dioxide. So what we get, and we get when it's about 0.5 weight% of the titanium content with pre-ceramic precursor, its surface free energy is below 30. Okay. However, its contact angle is not, well, it's not very, very hydrophobic, very effectively hydrophobic compared with the, other compound of the pre-ceramic precursor with fluorinated compound. Okay. Well, the Renzo equation shows that the surface roughness, a factor of surface roughness versus the the contact angle. Okay. And there's a reference shows that the stainless steel 316L stainless steel. Okay, and when this stainless steel modified by the fluorinated nanoparticle, its surface energy reduced, surface free energy reduced from 41.4 to 24.7. And it also reduced the dissolvent accumulations by 97%. 97%. This the evidence shows that the TiO2 or the fluorinated particles, the fluorinated particles has the effect, has the antibacterial effect. Okay. And this reference shows that this is the Bayes curve. The Bayes curve shows that when this surface energy within a range between 20 to 30, it has the lattice accumulation of bacterial adhesion. So this experiment with two types of bacteria. So one is E. coli, and the other is Aedes. Okay, these are two types of the bacteria being cultured on the substrate with different surface free energy. Okay, and show this Bayes curve. That's the surface free energy between 20 to 30 has the optimum antibacterial effects. And I'll show you this anti-corrosion effects. Okay. And so this black one shows the pure copper film. And And for this region, it shows the pure the polysilanze pre-ceramic precursor incorporates the fluorinated resin F340 with different composition. So what we get? So do you still remember we need a higher corrosion potential, right? We need higher corrosion potential and what? And the lower corrosion current. Okay, so do we have it? Of course, right? So from here, so this is the corrosion potential enhance, right? Enhance. Okay, and the corrosion current reduced a lot. Okay, and then you can see that after this the pre-ceramic precursor incorporate F340, its potential increase is higher than the pure precursor, right? Higher than that of the pure precursor. Okay, and then if we look at the higher cross-linking temperature, what's gonna happen? What's gonna happen? You see, for the 300 cross-link temperature, if we desire to get the higher corrosion potential and the lowest the corrosion current, we need the higher content of the fluorinated resin, right? This is the pure copper, and the red one is the copper coated, the copper foam coated with the pure precursor, and this one is the 10% weight of the fluorinated compound, right? And this potential increase and this potential increase, okay, and the current reduced, right? And the current reduced, okay. And when the temperature higher than 300 reach to 400 and 500, well, in fact, we cannot really tell the differences in between, right? We cannot really, distinguish this corrosion potential and the corrosion current with the different fluorinated compound, right? You already overlap. These Tafel curves already overlapped. Okay. So this is a direct evidence to show that the fluorinated compound decomposed higher than 300 Celsius. Even at 300 Celsius, well, we can figure out some clue that, well, this fluorinated compound might begin to decompose. Okay. Okay, then we compare with the with other metals or coatings, such as the high entropy alloy, different type of high entropy alloy, and the SS304. Okay, and we compare the sample that we made is this pre-ceramic precursor incorporated with 1 weight% of the fluorinated compound, crosslink at 300 and 200 Celsius. And we compare the corrosion rate, right? We can calculate the corrosion rate by the OWRK. Oh, sorry. We can calculate surface energy by OWRK, and we can calculate the corrosion rate by, let me show you the equation here. Okay, you can calculate the corrosion rate. Okay. Okay, so what's the result is that? Shows that, well, the sample that we made, the coating that we made has the lowest corrosion rate. Okay, has the lowest corrosion, even compared with the high entropy alloy, even the high entropy alloy has the stronger mechanical property, right? It's very hard, very strong. However, from the corrosion point of view, it's not really, it's really nothing. Okay, I mean, this high entropy alloy is nothing for the anti-corrosion. Okay, so just show you the thickness, okay, of this coating. And this shows the titanium dioxide in copper with this precursor. Okay, it's the rutile anatase structure of the TiO2. And the surface roughness for FM is about 0.5, no, 0.5 nanometer and 1, depends on the fluorinated resin incorporated. Okay, and this is surface roughness of the TiO2, 0.5 weight percent and 1.5 weight percent. Okay, and when the surface roughness is smaller than 1 micron, we can regard this surface as the ideal surface. That means it's the smooth surface. Therefore, the surface roughness factor can be neglected. Okay, that we have to consider this surface roughness. Okay, whether if influences its surface energy or not. If its surface roughness is smaller than 1 micron. Okay. And next, let's look at the mechanical property. I mean, surface property, surface mechanical property. By natal indentation, and the maximum load is about 1 millinewton, and we measure the indentation point array is 20 points. Okay, it's 20 points. 20 indentation points. So what do we get? We get the average hardness is higher with the fluorinated resin dopant. Okay, it's the fluorinated dopant. However, when the temperature higher than 300, its surface hardness drop substantially. Okay, and when this temperature reaches to 500 Celsius, its hardness increase substantially. Why? Because about 450 to 500, these polymers start to transfer to ceramic phase. That's the reason why the surface hardness increased a lot at 500 Celsius. And at that temperature, well, the fluorinated resin is nothing. It's useless. Because it's already decomposed. Okay. And the reduced modulus has similar trends that when the fluorinated resin doped, we see it has the higher modulus, and when the temperature reaches 400 Celsius, the modulus drop. Okay, modulus drop. Okay, this reference shows that when the surface doped with fluorine, in this case, it shows the fluorine gas doped, and its surface hardness and modulus will increase with increase the content of fluorine dopant at the specific limit, specific content. Okay, when the fluorine dopant is beyond that limit, and its surface property, hardness and Young's modulus, drop substantially. Okay, and also we compare with different substrate. Okay, previously we just spin coated this precursor incorporates the fluorinated resin, or diluted or incorporated with TiO2 and spin coating on the silicon. And whether it's functional with different substrate. Therefore, we compare with the medium carbon steel. We just have the same process, the same materials, the same compound, and spin coating on the medium carbon steel. And compare with that coating on silicon wafer. Well, while it's quite similar, there's no much difference. Okay. even the contact angle, water contact angle, and the surface free energy, well, it's almost no, there's no much big difference. Therefore, I can say, well, as most probability, it works for different substrate, metals or like silicon, glass, and so on, and so on. Okay, so the conclusion is that for the pure PSD, that's mean the pure pre-ceramic precursor, the contact angle increased from 94 to 180 with the increasing the cross-linking or product temperature. Okay, and when this product temperature is higher than 500 Celsius, the contact angle drop. Okay, and when this precursor incorporate with the fluorinated rinsing F340, and the contact angle increase 17% at the temperature between 200 and 300 Celsius. Okay, and the dilute in acetone, I mean the PSD, the precursor dilute with acetone, the contact angle increase. And the optimal ratio is 80 and 68% dilute in acetone. However, its surface energy is not the lowest. Even it's become higher. Okay, even it's become higher. And when this precursor incorporates F340, okay, this when we add this F340, its surface free energy reduced. Okay, and for this pure precursor heated at 200 Celsius, its surface free energy is about 32. And we add about 10% of this fluorinated resin, its surface energy drop to 28. Okay, 28. Even this precursor heat at 500 Celsius, this surface energy, well, still drop. Okay, still drop. Okay. And for this dilute acetone, the precursor dilute with acetone, we find this lowest surface energy is about 68% of the pre-ceramic precursor. It has the lowest surface free energy. However, it's still higher than 30, right? So it's still higher than 30, okay? And then we can find out the sample of the precursor incorporate with 10% of fluorinated resin has the lowest surface energy for this, this dual functional coating, anti-corrosion, antibacterial, or anti-fouling. Okay, and then if you just want to focus on the hydrophobic application, well, I will say maybe you just dilute with acetone. You can get the highest contact angle. Okay, according to the Bayer curve, we can speculate that the silicon-based polymeric film is antibacterial. And for this corrosion resistance test, okay, for this coating heated at 200 Celsius has the highest corrosion potential. And when this coating heated at 300 Celsius has the lowest current density, corrosion current density. Okay. And we have a conclusion that when this sample, when this coating crosslink at 200 Celsius, 200 Celsius, and whose property increase the hydrophobicity and the lowest surface energy and the highest corrosion potential, and whose hardness is higher than the aluminum. Okay, and this research I just want to emphasize that the contact angle of this research is not the highest. You can find tons of papers shows, oh, we have the highest contact angle, right? Right, you know what I'm saying? And in this research, I just want to focus on, for this coating, I can modify it. I can modify with the different function, depends on what's the application that I need. You know what I'm saying? I don't want to reach the highest contact angle. Well, for me, that's meaningless. Okay, for the materials applications, or for the industrial applications, we have to find out the most economically and most functional, but not, no, we need the highest some property, which is the highest. You know what I'm saying? We need a multifunctional properties. But however, maybe, or each properties, each property is not the highest, or it's not the best. However, for this coating, can has the multifunction applications. Okay. Okay. So my research, this research will be ended here. So if you have any questions, you can just email me or leave your message and the YouTube channel. Okay. Thank you. Bye bye.